Welcome to today's Explainer. We're going to follow the invisible, literally monumental journey electricity takes to keep our modern world running. It's kind of like the air we breathe, right? We barely even notice it until, bam, it's suddenly gone. You walk into a dark room during an outage, flip a useless light switch, and suddenly realize your entire modern life depends on this invisible force. So today, we're tracing exactly how that power travels from its moment of creation all the way to your bedroom wall.
All right, let's just take a bird's-eye view of this massive supply chain. It really helps to think of the electric current as a traveler on a highly technical cross-country road trip. We start on the generation side, where the power is literally born. Then we hit the road, traveling across the vast distances of the high-voltage transmission network. Think of these as the interstate highways of our grid. Finally, we navigate the local distribution network, which is more like the side streets and neighborhood roads, right down to the specific end use in your home.
Here's the roadmap for our explainer today. We'll look at generating alternating current, hitting the high-voltage highway, the magic trick of transformers, navigating the local distribution grid, and finally, powering your home.
So, Part 1. Generating alternating current. Our hero's journey kicks off right at the power plant, where mechanical energy gets converted into raw electrical power. Whether it's a giant hydroelectric dam spinning a water wheel or a massive steam turbine powered by coal, natural gas, or a nuclear reactor, the core mechanism is almost always a spinning electromagnetic generator. But here's the cool part. Commercial generators don't just produce a single stream of power. They output three-phase alternating current. If you looked at this on a graph, you'd see three separate electrical currents offset in time by exactly 120 degrees. Why three? Well, in a single-phase system, there are moments when the power wave crosses 0 volts. But with three phases, at any given microsecond, at least one of the phases is nearing a peak. It creates this incredibly even, balanced output of power that's absolutely perfect for heavy industrial motors. This power then leaves the plant on 4 wires, 3 carrying those active phases and a 4th common neutral ground wire.
Now for Part 2, the high-voltage highway.
As this newly generated electricity leaves the plant to hit the interstate highways of our grid, it immediately comes face-to-face with its natural enemy, joule heating. See, when current flows through a conductor, like a super long metal wire, a chunk of that precious energy is lost as heat. This is due to the internal friction, or electrical resistance, of the wire itself. If we actually tried transmitting electricity at the relatively low voltages it's generated at, say 5 to 35 kilovolts, across hundreds of miles, we'd suffer massive, crippling energy losses long before it ever reached a city.
The crucial point is right here in the physics with Joule's law. Power loss equals the square of the current multiplied by the resistance. Because energy loss increases with the square of the current, minimizing that current is literally the absolute best way to survive this highway journey. If we drop the current, we exponentially drop the amount of heat lost to the environment. But you might be wondering, how on earth do we drop the current while still delivering the massive amount of power a whole city needs?
Well, we achieve that low current by jacking up the voltage. Utilities use colossal transmission towers to push electricity at extra high voltages. By stepping the voltage all the way up to 115, 345, or even 765 kilovolts, the current is proportionally decreased. This neat trick allows our traveler to cruise for hundreds of miles through relatively thin transmission cables with minimal thermal energy loss.
Which brings us to Part 3, transformers and their magic trick. To actually manipulate these extreme voltages, the grid relies on the absolute magic of electromagnetic induction. This happens inside a transformer. At its most basic, a transformer has 2 separate coils of insulated wire wrapped around a shared iron core. When alternating current flows through the primary coil, it generates a fluctuating magnetic field in the iron, which then induces a brand new voltage in the secondary coil. By simply altering the ratio of those wire coils, we can change the voltage. A step-up transformer at the power plant has fewer turns on the primary coil than the secondary, efficiently boosting the voltage for the long highway haul. Conversely, a step-down transformer has more primary turns, which reduces the voltage for the local off-ramps as it nears your town.
Moving right along to Part 4, the local distribution grid. As the power finally approaches your specific community, it has to get off that transmission highway. We obviously can't have 500,000 volts running right past your front porch, right? Instead, it goes through a carefully orchestrated step-down process.
First, regional substations drop those extreme highway voltages down to sub-transmission levels, usually around 34 to 69 kilovolts. Then, local distribution substations step it down again to primary distribution circuits. This is typically around 7,200 volts, which is exactly the voltage running through the lines you see on the wooden poles in your own neighborhood.
Now, a truly surprising fact about this local distribution is that the grid literally uses the Earth itself as a giant return path for electrons. Think about that for a second. The dirt, the rocks, the groundwater beneath your feet, they're all part of the electrical circuit. If you look closely at a wooden utility pole, you'll probably spot a bare copper grounding wire running straight down the side. It doesn't just stop at the grass either. The utility company buries it in a coil 6 to 10 feet deep to ensure a direct, solid connection to the planet. Crazy, right?
And finally, Part 5, Powering Your Home. Our electrical journey arrives at its destination to do the actual work of powering your daily life. You've definitely seen these before, that familiar gray metal cylinder mounted on the pole outside your house, or maybe a green metal box sitting on the ground. This is the final step-down transformer. It takes that 7,200-volt neighborhood line and reduces it to a split-phase residential standard. It actually divides the output into two active 120-volt lines that are 180 degrees out of phase with each other, plus a neutral ground wire. These three wires are what physically enter your house right through the electric meter.
This split-phase setup explains perfectly why your house has different types of outlets. Your standard appliances, like a bedroom lamp or a phone charger, only tap into one of those 120-volt lines and the neutral wire. But your heavy-duty appliances, we're talking central air conditioning, water heaters, or electric dryers, they need way more juice. They connect across both active lines simultaneously, drawing the full 240-volt potential difference to do the heavy lifting.
But what happens when this immense, highly charged network faces a physical threat? What if a wire inside your living room wall gets chewed by a mouse, or someone accidentally vacuums up a lamp cord, cutting it and connecting the power directly to ground?
Well, without safety devices, a direct connection to ground would cause the wires inside your walls to pump so much current that they'd instantly act like the heating elements in an oven and just burst into flames. Luckily, inside your house, we stop this using vaporizing fuses or tripping circuit breakers. A fuse uses a thin piece of foil that physically vaporizes to instantly kill the current during an overload. Circuit breakers, on the other hand, use the heat of the overload to mechanically trip a switch, which is exactly why you can just pop down to your basement and reset them.
Out on the larger grid, the stakes are even higher. Utilities are constantly deploying hardening measures to protect against falling trees, hurricanes, and floods. They clear vegetation, bury lines underground, and use breakaway connectors that snap off before a falling tree limb can literally rip the electric meter right off the side of your house. On the high-voltage highway, they strategically place extra-heavy dead-end transmission towers. So if a violent storm takes down a weaker suspension tower, these massive anchor towers are designed to absorb all that tension and stop a catastrophic domino effect collapse of the whole line.
So now that you understand the monumental physics keeping your lights on, we have to look ahead. For over a century, this system was a simple one-way street from the massive power plant directly to your home. But today, with distributed energy resources like rooftop solar panels and home batteries, your house is actually starting to send power backward onto the grid. As our energy generation becomes decentralized, how will this vast, rigid infrastructure adapt to a future where millions of homes are both consumers and producers? It's genuinely the greatest engineering challenge of our time, and definitely something to think about the next time you flip a light switch.